This is the first lecture of Chapter 11, and Chapter 11 will be entirely devoted to the argument of diagonalization of matrices. So here we'll talk about motivations. In lecture 6.6 and 6.7, we have introduced the so-called elementary operations on a matrix. The idea was to simplify a matrix in steps, while leaving its rank unchanged. Among other procedures of simplification of matrices is so-called the similitude. Definition: two square matrices of the same order, A and B, are similar if there exists a matrix P invertible such that B equals the inverse of P times A times P. And what we are trying to do is to see if among all the matrices of the kind P minus 1 times A times P, with P varying among all the invertible matrices, we can find one which is particularly nice. In that case, we will say that A and B will be similar matrix, so A will be similar to a particularly nice matrix. Let's see what we mean exactly with particularly nice. As the word mean, two similar matrices share many fundamental properties. For example, they have the same rank. They have the same determinant. If A is invertible, B minus 1 equals P minus 1 times A minus 1 times P. If F is a homomorphism from Rn to Rn, and A is the associated matrix of F with respect to a choice of two bases, Vj and Vi, then there exists a basis, Wi, in Rn such that the associated matrix with respect of Wj and Wi equals to B. And we have shown these in lecture 9.6. Arguably, the simplest matrices are the diagonal matrices. So what is a diagonal matrix? Definition: let D with coefficients Dij be a square matrix. Then D is diagonal if Dij is 0 for each I different from j. So a diagonal matrix specifies its elements outside the diagonal, not along the diagonal. Along the diagonal, a diagonal matrix can have any scalar. There is no restriction. But outside the diagonal, it must be 0, identical to 0. These facts show that given a square matrix A, it is very reasonable to wonder whether A is similar to a diagonal matrix D. That being the case, for many intents and purposes, A can be considered a diagonal matrix then. Definition: a square matrix A is diagonalizable if there exists a matrix P invertible such that P minus 1 times A times P is diagonal. That means that A is diagonalizable if it is similar to a diagonal matrix. This is one of the cases for which the definition is useless to establish in practice the defined property, except in trivial cases. For example, if A is diagonal itself. So one may wonder whether a diagonal matrix is indeed diagonalizable, and of course the answer is yes, otherwise there would be a contradiction in terms of meaning of the words. Lemma: diagonal matrices are diagonalizable. Proof: in the definition, just take P to be the identity. In that case, this becomes the identity, this is the identity, so this triple product is just A, but A itself is diagonal by assumption.